Hello everyone. So welcome to the second lecture of Organometallic Chemistry. So in the last class we talked about the introduction part of organometallic chemistry, and then we talked about the different types of ligands involved in this organometallic chemistry, and then also we discussed about the metal carbonyl complexes, polycarbonyl complexes, and some synthesis of the carbenes like the Strock carbene, Fischer carbene, all these things and their metal complexes. And also we talked about the fluxional behavior of metal carbonyls and some of the square planar complexes. So today we are going to discuss about oxidative addition reaction, reductive elimination reaction, beta hydride elimination, alpha hydride elimination, migratory insertion reactions, and after this we will move to the metal arene complexes and the ligands involved for the synthesis of these complexes like cyclobutadienyl complex, cyclopentadienyl complex, cycloheptatrienyl complex, or cyclooctatetraenyl complex, and also π-allyl and some enyl systems. Okay, so let's start with the oxidative addition. So what is oxidative addition reaction? So oxidative addition reaction is a reaction in which the metal oxidation state, the electron count, and the coordination number increases by 2. That means, so here I can take the laser pointer. So here we can see that we have a metal complex here, LNM, and it oxidatively adds to this AB compound, to this bond, and we are getting this LNMAB complex. So here if we see that here the oxidation state of the metal, if it is 0 then it will go to +2, if it is 1 then it will go to +3, if it is +2 then it will go to +4, and so on. And the electron count, if we count the valence electron, including the electron are like donated by the ligands, we will see that this complex, the electron count will be increased by 2. And also the coordination number, whatever it is for the parent compound, the product compound will see the coordination number will increase by 2. So such kind of reactions, we can call them oxidative addition reactions. So here are some requirements, that this metal should have the vacant shell so that it can oxidatively add to this AB. And also, so so this after the coordination, so I mean here, so it is, since it is increasing the coordination number by 2, so it should have also this space or the size of the metal atom should be like that it can accommodate the 2 more ligands in its coordination sphere. So let's have some example of this oxidative addition reaction. So here we have Vasquez complex. So this is a very ideal example of oxidative addition. So here the iridium, the oxidation state of iridium is 1 here, +1. So after the oxidative addition here, if we react it with the hydrogen, we will get the iridium hydride complex, and here the oxidation state moves to +3 from +1. And here if we count the number of valence electron, so iridium 1, it's a like D8 system, and for the 4 ligands we are getting 8 more electrons, so 8 plus 8 equals to 16 valence electron complex. But when it is oxidatively added to the hydrogen, after this getting octahedral complex, here the iridium is, so oxidation state is increased by 2 and coordination number is also increased by 2. Now let's see the valence electron count. So here iridium 3, that means this is D6 system, and the 6 ligands are donating 2 electrons each, so in total 6 multiplied by 2, so 12. So and this iridium 3 means D6 system, so 12 plus 6 equals to 18 valence electron complex. And the 18 electron rule, that is the effective atomic number rule, it says that if, so this type of complex, if the valence electron count shows 18, then this complex will be stable. And this oxidative addition also can be done with the oxygen to this, the valence electron, like 16 valence electron complex iridium 1, and we can get this type of, so oxo complex, where this electron count also will be 18 for this complex. And obviously we can see that the coordination number and the oxidation state is also increased by 2. So here we can see that, so this silane, trimethyl silane, also can add to this iridium 1 complex to give this octahedral iridium 3 complex, which also satisfies this EAN rule. Now, if we react this viscous complex with the chlorine, we will get a dichloride complex. So this is like a trans complex here, and this is also 18 valence electron complex. So accordingly, we can also react it with the HX, that is the hydro like halide like HCl or HI, HBr. We can also synthesize this 18 valence electron iridium 3 complex. And similarly, also the iodomethane can react with viscous complex to get this methyl and iodide iridium 3 complex. So here is the reaction mechanism of this oxidative addition reaction. So there are some like proposed and some proved reaction mechanism. So here the first one is a concerted mechanism. It's a concerted pathway. So here, if we take this complex as the viscous complex, that means I can take the laser pointer here. So if this L is triphenyl phosphine, then we can see that. So here this is triphenyl phosphine. So this is chloride, that is -1 charge, and so the charge is on the iridium here, so +1. So this iridium complex, this is 16 valence electron complex, and when it adds to the hydrogen, so first one interaction between the hydrogen with the iridium occurs, and then in the next step, that is the concerted pathway, we get the product. So we are getting the product basically in one step. So that is the concerted pathway. So direct insertion of this metal into this HH bond. And also this, this is iridium 3, and this is coordination number also increased by 2, and oxidation state is increased by 2, and the electron count is here 18, that is also increased by 2 when we compare it with the square planar starting material. Now the next mechanistic pathway, that is the SN2 mechanism, that is obviously not concerted. So at the first step, so this complex adds to the methyl, and then methyl cation adds to this iridium center, and in the next step, this iodide adds to this iridium center to give this octahedral complex. So this is basically SN2. So substitution nucleophilic like bimolecular. Okay, so now let's have some overview of this oxidative addition reaction. So we have seen that we can get the product which can be explained by the concerted mechanism, SN2 mechanism, and also we can also explain the oxidative addition reaction by radical and ionic mechanism. And most importantly, we can see that when it follows the concerted pathway, we always get the cis addition, like the addition to the hydrogen, addition to the alkane, or addition to the silane compound. It always gives the cis addition. But when it adds to the alkyl halide or chlorine, bromine, iodine, we always get the trans. Most of the times we get trans addition product. And for the radical mechanism, we can also do it with the alkyl halide or the tin halide. And for the ionic mechanism, we can explain it for the halide, like the HX product, that is a HCl, HI, or HBr reactions. So now we have another reaction, that is the reductive elimination, which is exactly opposite to the oxidative addition reaction. So in the previous slides, we have seen that this reaction, so this metal complex is added to the AB, and when it is giving this product, so we call it the oxidative addition reaction. But the reverse reaction, which is from like the decomposition of this product to this AB1 and this ln basically M. So this one here, so here the oxidation state, electron count, and the coordination number is decreased by 2. So each of them is decreased by 2, then this reaction is called reductive elimination reaction. Like here, so for the oxidative addition, when we react this metal complex with the alkane, we got this product, but the reductive elimination is just the other way around. The the decomposition or the elimination basically to get this the starting material here in this case. So for this ln mr2, we can get this ln m plus rr. So this here basically alkane we are getting back from this reaction. So here this is also ln mh and cor, which is giving after reductive elimination, we will get this ln m plus rcho, and accordingly we can get the other products by this reductive elimination reaction. So here are some other elimination reactions. The most famous one is the beta hydride elimination. So here we can see that if the metal is coordinated to any alkane, and if this alkane has any beta hydrogen here, as we can see the green one, the beta hydrogen, or basically all three are beta hydrogen, but here the H is close to the metal, and here if the metal has a vacant orbital, so which can take the hydride, take this hydrogen as hydride and forming one double bond here, and then this metal can bound this alkene product as a like a pi bond here through the pi bond. So this reaction is called the beta hydride elimination. That means here the beta hydrogen is eliminated to give this hydride, and here the metal is bound to the pi bond of this alkene. The next one is the alpha hydride elimination. So here the hydrogen from the alpha carbon, so this is moved to the metal giving an hydride, and here so it forms a double bond from the metal. So we have a metal double bond carbon bond, and we have, if it is a chain, then we have other R group. So this is, we can see in the Grubbs catalyst, this type of bond is there. And the third one is the carbonyl elimination reaction or the decarbonylation reaction. So here, if we have one, like the metals would have one vacant orbital, which can take the migratory alkyl group here. But after this reaction, so we see that this R is migrating to the metal, and here the carbonyl, which is so now an acyl, but after the reaction we will get the CO as like isolated, like the terminal CO, and we will get one metal alkyl bond. So this is called the decarbonylation or the carbonyl elimination reaction. So next is the migratory insertion reaction of this organometallic compound involving carbonyl. So here we can see that, so this is the reactant what we have here. So M is having an MX bond, and also one terminal carbonyl is there in this complex. So in the last slide we can see that, so when we were hitting, so this product, so I can take the laser pointer here, when we were hitting this product, so this X was migrated to this vacant orbital of this M, giving one terminal CO like this. So this is the the reversible reaction of this this basically the carbonyl elimination reaction. So here if we have a compound which has the MX bond and also MCO bond, and after this 1,1 migratory reaction or migratory insertion reaction, so here X will migrate to the carbon of this carbonyl group, giving one acyl type of product, and also generating one vacant coordination site for this metal. And for this 1,2 insertion reaction, we can see that this X group can migrate to this beta position, and this carbon will bond to the metal, giving making this one an alpha carbon like this, and so this also gives an empty coordination site for this metal. So here after the reaction for this 1,1 migratory insertion or 1,2 migratory insertion, we can see that metal is having one empty coordination site and also the 2 electron vacancy. So this is a very important reaction in organometallic chemistry. So we can see in the next slide. So as I was telling that here is the famous example of carbonyl insertion reaction done by Calde-Rajot. So in this reaction, so here we have magnesium complex, and here we have one like metal alkyl bond. So here alkyl is the methyl group. So when we react this with the carbonyl group, so we get this product. And if we take this carbon monoxide is a labeled carbon monoxide like 13 CO, so we see that the carbonyl like the labeled CO is coming to this position. That means, so first we have this alkyl migration to this alkyl is migrated to the carbonyl carbon atom, given one vacant coordination site here, and then when we bubble the carbon monoxide or labeled carbon monoxide in this reaction mixture, so this comes to this vacant coordination site, giving this product. So this reaction is called like the carbonyl insertion reaction. So whenever we say carbonyl insertion reaction in presence of metal alkyl bond, we need to mean that the first alkyl migrates, and then the incoming CO takes the vacant coordination site like what is shown here. So in the next part, we will talk about the sandwich metal complexes and the ligands needed for this reaction. So needed for the synthesis of these complexes. So these sandwich metal complexes, the name came after the sandwich what we eat in our breakfast or snacks or whatever. So here we can see there. So this is the sandwich like the one braid here, and at the bottom we have another braid likewise here. So, and in the middle we have some like some salad or tomato or any other potato tikki or anything. So similarly to this complex, we can also synthesize the chemical at our laboratory. So we can see that this is the compound, very famous compound known as ferrocene. So here we have two ligands. So this is one cyclopentadienyl at the top, and this is the second cyclopentadienyl at the bottom. And here, so each cyclopentadienyl is -1 charge, and so here the iron is 2 oxidase instead. So iron is iron 2, that is the D6 system. So from the 18 electron rule, so we can calculate the valence electron here, since we know that the Cp minus, that is the cyclopentadienyl minus, it donates 6 electrons. So from the 2 Cp minus we can get like 12 electrons, and the iron 2 is D6 system. So 12 plus 6, this is 18 valence electron complex is this ferrocene. So this is a highly stable complex, and we can also see that it does not react easily with any nucleophile or electrophile easily. So we need some reaction condition, and then only it can react with this like harsh condition. So here we can see this is the structure of this ferrocene, and this is the ideal example of the sandwich complex. So this is the metal which is sandwiched between this Cp pi plane of these two Cp. So here we have another sandwich complex, but here the pi plane is not cyclopentadienyl, but instead we have a benzene ring here. So this is chromium 0 complex, since benzene is neutral. So we have two benzene at the top and the bottom, and here the chromium is chromium 0. So chromium 0, that means this is also D6 system, and since chromium, this benzene also can give can donate 6 electrons. So 6 6 6, also 18 electron valence electron complex is this chromium complex. So this is also highly stable complex. And here are some other complexes. So this is called bent sandwich. We will discuss later about these complexes, and these are called half sandwich complex, and this is another type of metal sandwich complex. Here we can see that instead of one metal we have two metals, and also we can see, so this is another complex, that this is a triple decker complex or nickelocene complex. So let's talk about the ferrocene first. So this is like a path-breaking discovery of this sandwich compound. So Paulson and Kelly, so they were doing some reactions with this Cp magnesium bromide, that is the cyclopentadienyl magnesium bromide, and they were heating with iron chloride, and they were expecting the product of this fulvalene. So here, but instead of getting fulvalene, so they got some product which is not matching with the fulvalene, because here the fulvalene is not perfectly aromatic. So if we break this bond, not fully breaking, but if we just isolate this bond, like the break one bond and making this one minus and this one plus, then this will be a 6 pi electron system cyclic ring, and this is 4 pi electron system cyclic ring. That means this is aromatic and this is anti-aromatic. So as a whole, so if we make it as reverse, so this will be aromatic and this will be anti-aromatic. So this is not a very stable complex, but when they did this reaction, so they got very highly stable complex, but at the beginning they could not understand what is this product. But later on, Geoffrey Wilkinson, Fisher, so they worked on this complex and they found out what is the structure, and they found out, okay, this is not basically the fulvalene, but this is basically this type of like iron 2 is sandwiched between the cyclopentadienyl ligands. So they name it like the ferrocene. And later on, so these complexes, the similar type of complexes have also been synthesized with other metals like cobalt, nickel, or any other, also some palladium. So, and these complexes have been published in high impact journals. And also for their discovery, so Wilkinson and Fisher, they got Nobel Prize in 1973. And Woodward got also like a Nobel Prize in 1965 for his contribution to the art of organic synthesis. Yeah, so this is another big question, that why should we synthesize ferrocene, or why should we study about ferrocene? The answer is ferrocene can be used in many applications. So the first one is ferrocene can be added as a fuel additive, so which actually helps us to generate less smoke. So it can be added as a like the smoke suppressant, and also it can also obviously it is a fuel additive, as can also be an anti-knocking agent, and also ferrocene is a good catalyst precursor. So by modification of the ferrocene backbone, we can generate many catalysts. Okay, so here is the ferrocene powder. We can say this is orange or yellow orange powder, and we can also easily crystallize ferrocene. So here are the, if we sublimate ferrocene, we can get this type of like nice crystals. Yes, so here is the cyclopentadienyl ligand, which is needed for this ferrocene synthesis. So this ligand actually shows different type of coordination behavior. So here we can see the cyclopentadienyl, that means here C5H5 minus here, and it can simply coordinate to an eta 1 fashion, that is the heptacity 1. So it can also coordinate to the metal by heptacity 3, that is the eta 3 coordination. Like here, only these 3 carbon atoms can be bounded to the metal, but the other two, like this double bond is not bounding to this metal. But another coordination that is the most popular, most common, is this: the all 5 carbon atom of this C5H5 unit is bounded to the metal, giving one eta 5 coordination complex. So here are other sandwich metal complexes and other ligands we can use for the synthesis of sandwich metal complexes. Like here we have seen already the ferrocene, which is involving like the cyclopentadienyl ligand. We can also use benzene, like the chromium. So chromium diarene complex. So also we can use the cyclooctatetraene as a ligand for this for the synthesis of sandwich metal complexes. And also we can use like the C9, like the cyclononatetrienyl complex. And so these all are basically homoleptic metallocenes. Like basically here both the ligands are same. So here is the CP, this is the benzene, and this is also benzene. This is cyclooctatetraene, this is also cyclooctatetraene. This is the similar ligand. So this is the 9-member cyclic ring. This is also the like 9 carbon cyclic ring. So all are homoleptic metallocenes, but we can also synthesize some heteroleptic metallocenes. For example, here this is like a cyclic like a square type of ring. This is like butadiene, or this is this complex is basically one side is cyclobutadiene and this is the CP. So this is heteroleptic. So like 2 different types of ligand are used to this for the synthesis of these heteroleptic metallocenes. And we can also use this benzene and CP for the synthesis of another sandwich type of complex. Or here this is 7-member ring, this is 5-member ring, this is 8-member, this is also 5-member, and this is 9 and 8. So these are the varieties type of sandwich metal complexes we can use. But yeah, we can see that, I mean, we can synthesize, but sometimes their stability varies. So it is not that all are very highly stable complex, but only if it fits to this 18 electron rule, they are highly stable. Some other complexes also stable, but most of these metallocean compounds are very, very sensitive towards air or moisture. So either we need to keep them under inert atmosphere or in the glove box conditions. So here other sandwich metal complexes also using like here this allyl ring. So here also the allyl, we can see that this is bonded to the center, means this is the pi bond. So here this is the delocalized. So here allyl is eta 3 condition, and this is also like ferrocene, the normal one, and this is as we have seen before, this is the chromium sandwich metal complex, and this is the uranium cyclooctatetraenyl sandwich metal complex. So here are the molecular structures of these complexes. We can see that this is cobaltocene, which is formed by the cyclobutene or cyclobutadienyl ring, and this is a CP, cyclopentadienyl ring. And so this is basically ferrocene, what we have seen before, and this is manganosine, but this is CP, and this is benzene, and this is like the chromium with benzene, and this is another chromium sandwich complex. So here this is CP, and this is, we can see that this is cycloheptatrienyl ligand. And we have other type of sandwich metal complexes here. So now, for example, here we can see there, so this is not exactly similar to the first row. So because here we can see that this is the ideal sandwich metal complex. So here the metal is sandwiched between these two pi plane, but here this is sandwiched but like a bent sandwich. So these all complexes are actually called bent sandwich metal complexes. So this is tantalum complex, this is molybdenum, this is titanium, and this is the rhenium complex. So these all are basically, so this is rhenium, so this is -1, this is also -1 charge, and this is chloride -1 charge, so this is rhenium 3, and in this case this is titanium 4, this is molybdenum, also like this is Cp1 minus, this Cp is also 1 minus, and this is hydride, so molybdenum also here oxidation state is 4, and titanium, so tantalum here, this is tantalum 5. So also we can see that tantalum 5 is also used for the generation of rock carbines. And other type of sandwich complexes, that is here at the last row, and since we can see that here we are like missing the bottom ring, so these rings, these complexes are called half sandwich metal complexes. So this metal is sandwiched between this one ring here, and this the bottom one is basically the CO. So this is also called piano stool structure. So piano means here we have this the upper cover, and this is the metal, and here the legs. So this is also called piano stool structure. So yeah, these are also called half sandwich structure. Now we can see some of their synthesis. So these are some synthetic procedures to synthesize metallocenes. So if we react to iron 2 chloride in presence of Cp and in presence of like diethylamine base, we can generate like the ferrocene, and this chloride, the salt, will be like remain as a byproduct. So here the ruthenium chloro, like the water, like the complex can react with Cp in presence of zinc. It can give us this Cp2 ruthenium metallocene, and like this Cp like C5H8 will remain as a byproduct. And accordingly, we can also synthesize this thallium metallocene. So but this since this is poisonous, so nowadays this is like prohibited to use this compound. And also we can synthesize this piano stool, the half sandwich complexes, the manganese, by this reaction of Cp like thallium cyclopentadienyl complex with the like manganese chloro-pentacarbonyl complex. And if we heat this mixture, we can get this half sandwich complex Cp manganese like tricarbonyl complex. And most importantly, so when we use this Cp, so this Cp actually does not stay as a monomer here, so it actually stays as a dimer here like this. So if we want to use this one for our like the synthesis of our ferrocene, so first we need to crack so this dimer to the monomer here. So this cracking can be done at 180 degrees centigrade, and then you need to distill this one to get this pure monomer, and then you can react with sodium to get sodium Cp. So this sodium Cp can be used with this iron chloride, ruthenium, or any other like the osmium or any other metal salt to get this metallocene. So at the first slide, I have informed you that so this ferrocene is a very stable compound. So since it satisfies the 18 electron rule, but still we can do some reactions with the ferrocene. So ferrocene can undergo electrophilic substitution reactions. You can take the laser pointer here, and many of its reactions are faster than the similar reactions of benzene. So here we can see that this ferrocene can be oxidized in presence of iodine, and we can generate ferrocenium cation, and I2 can form I3, and it can just attach to it to give a salt. So this ferrocene can also react with HbF4 O82 this complex to give this ferrocenium tetrafluoroborate salt, and also accordingly it can also react with ammonium PF6 in presence of ferric chloride, so it can oxidize ferrocene to give this ferrocenium hexafluorophosphate salt. And like other reactions, like here acetylation reaction, we can synthesize this acetyl ferrocene compound by the reaction with the acetic anhydride. And if we react with like the excess of this is acid chloride, and in presence of aluminium chloride, which is a Lewis acid, we can generate this dye substituted acetyl, like diacetylferrocene. So one thing we need to note that here the diacetylation does not occur at the one ring but the two rings. So this is 90% majority of the compound. We will get this diacetylferrocene ring, and simply we can do the column chromatography to purify this product. And so this is highly not highly stable, but this is very stable compound, like a bench stable compound used for. We can also oxidize this acetylferrocene and we can generate some other oxidant. So these are some other reactions involving ferrocene here. So if we react this ferrocene with mercuric acetate, so we can deprotonate this proton here, and then mercuric acetate can attach to this group. So followed by, when it reacts with lithium chloride, it generates HgCl. So this is mercury chloride ferrocene compound. So this is also, we can do the Manich reaction on this ferrocene, and we can generate this CH2N Me2 or in alkyl, like alkylamine. And if we do the lithiation reaction, so we will also talk about this lithiation reaction in the later slide. So here, if we deprotonate one proton by this by the addition of tertiary butyl lithium, and also we can functionalize this ring with the addition of any other reagent. So here also we can add TMEDA to stabilize somewhat this product. So after the monolithiation of this ferrocene, we can synthesize so many other like the ferrocene derivatives like here. So if we react it with the silicon tetrachloride, we can like synthesize its like trichlorosilane derivative. If we react it with sulfur, then it is SLI. If we react it with the carbon dioxide and then acid, then we can generate the, like monocarboxylic acid. Then also like the ester, boron ester, we can synthesize some boric acid. And this is also, if we react with iodine or bromine, we can also synthesize its ferrocene iodide, like here, or the bromo compound. Or if we add also like sodium cyanide, we can also synthesize its cyano derivative. And then if we take the dilithiated version, then also we can synthesize like the dicarboxylic acid. This is diboric acid, like dibromoferrocene. This is like the dimethyl, like the silane, and also this is disubstituted like bisphenyl, like the phosphine compound with this ferrocene. So if you want to study in detail, and also if you want to like know more about these complexes, so you better read these books, as I have also informed in my first lecture, that the first book I recommend, that is the basic organometallic chemistry by B.D. Gupta and A.J. Elias, and the second or the third books are basically by Crabtree and Elston Broich, and the fourth one is the must-read book for the inorganic chemistry, that is the principles of the structure and reactivity in organic chemistry by Hui Mehdi, like Kitter Mehdi. So in this today's lecture, we have covered oxidative addition, beta-elimination, the reductive elimination, alpha-elimination, all these reactions, and also like CO insertion reaction, migratory insertion. We have also discussed about the sandwich and half sandwich and bent sandwich metal complexes, and also like pi acid, like pi ligands, pi-planar ligand, and enyls like cyclobutadienyl, cyclopentadienyl, cyclooctatetraenyl, or tetraenyl complexes, all these things. So if you want to know more about these complexes, you can also comment in the comment box. So I'll be happy to make another video in detail. So thank you very much.